CodeFast comes with a variety of CLI options. These options expose built-in debugging, multiple ways to execute scripts, and other helpful runtime options. Running the node command without arguments starts a REPL, read, eval, print, loop. I use node as a REPL very often. It's really a convenient way to quickly test JavaScript, especially when you're already in a terminal. So when you hit enter in a REPL, it reads the command, executes it, and then prints its result to the screen. And then it waits for your next command. That's why you don't need to use console log in the REPL, and sometimes you'll see it outputs undefined because many commands like defining a variable here don't have any output. One of the most useful features of Node's REPL is the autocomplete. If you just tap on an empty line, you get this big list, which is equivalent to tapping on the global object. Autocomplete works on any object. For example, say that we have an array variable like this one. Doing a dot and then tab on that gives you everything you can do on the array object. Of course, this tab autocomplete will work when you type some characters too, and if there's only one method, it will autocomplete it for you. That's why it's called autocomplete. Autocomplete works in your terminal with all the built-in commands, and I even configure commands like git to have autocomplete. I now simply cannot live without autocomplete. Not only because I'm a lazy typer, which I am, but because I get instant validation on the things I want to type. The autocomplete list for the global object is a special one. This is all the top-level functions and modules available in Node. In a Node REPL, a lot of the native Node modules are preloaded already and available on the global scope. This is not the case when you execute a normal script. If you want to see just the actual properties of the global object, you can just print them with a console log line. Node's REPL remembers the lines that you previously tested, and you can navigate to them with the up-down arrow. However, my favorite feature to look up a previous command I type in a terminal is the reverse search feature with Ctrl R, but that's not available in Node's REPL. However, we can use this readline wrap utility to get that feature. You'll have to install this utility separately, but once you have it, you can use Node this way. You'll have to specify the Node noReadline environment variable to disable the built-in readline and then use the readline feature and many others from the rlwrap utility. And now we can use reverse search with Node REPL. Another helpful REPL feature is the underscore. You can use it to access the last evaluated value. This is handy if you want to capture this last output in a local variable like this. Node's REPL has special commands that all begin with a dot. So .tab will get you a list of those, and .help will give you a description of each. Let me mention a few handy ones. .break can be used to break out of multi-line session. Say you pasted something incomplete and you're stuck in the multi-line mode. .break will simply get you out of it. .load can be used to load another script into the REPL session. You can use the .save command to save the history of your REPL session into a file. Very useful after a long session in REPL. The .editor command gives you a multi-line editor for your REPL commands. So you can use it, for example, to define a function as if you're writing it in an editor. You can Control D when you're done, and everything you typed in the editor will be evaluated. This is much better than the default multi-line mode in the REPL. Node has a built-in REPL module, which is what it uses to give us the default REPL mode, but we can use this module to create custom REPL sessions. We just require it and invoke the start function. The start function options can be used to customize the session. We can customize things like the prompt, the readable and writable stream. For example, we can have a REPL that works with a socket instead of a standard in-out. We can customize the eval function, colors, and many other things. Here's an example of a custom REPL where I customized two options. First, don't print out the undefined values, and use strict mode. Both of these options I find helpful. We can also control the REPL's global context. So if you want a REPL where you preload your favorite libraries, just add them to this context object like this. Now Lodash will be available globally in this custom REPL. Let's now take a look at some of the options we have for the node command itself. We've already seen the V8 options, which lists a lot more options that we can use with the node command. But some of the other options here are important. The -c is helpful, for example. We can use the -c in a pre-commit hook to make sure that we don't commit anything with bad syntax. We've also been using the -p option, which is another practical one. It evaluates a string and prints the result just like in REPL mode. For example, here's a quick command to figure out what architecture Node is running on, or the number of processors Node sees. The -r option can be used to preload one or more modules before executing the script. This is useful to preload a certain customization without modifying the code itself. Say, for example, you want to run the code keeping track of all registered timers. You can preload a script that modifies all timer functions to do so, and you can similarly modify loggers or any other globally accessible feature. The list of arguments you supply after the command line can be used to supply the process with direct input. All the arguments can be accessed using the process.argv, which will be an array containing all of them. The first argument in the process argv array is the node command itself, so usually this is to be excluded. Note that all the values in process argv are strings. The one and only true global object in Node is called global. When we declare a top-level variable in Node, like the answer variable here, that answer variable is local to the util.js file, and we can't access it from other files, even after requiring the util.js module. However, when we define answer on the global object, the index file, which requires the util.js module, can now access that globally declared variable. It goes without saying that we should try to avoid defining things on the global object at any cost, but it helps to understand all the built-in properties defined on the global object. You can quote me on this. You're not a Node expert unless you recognize and know how to use everything you see in the global list of objects in REPL mode. In fact, if you do know everything in this list, this course is probably not for you, because this list represents most of what we will be talking about in this course. But you should recognize some of the items here, like the object, string, array function, to name a few. All the familiar top-level JavaScript functions that you know and love are listed here. But there are a lot more to discover. Note that most of these modules have to be required in a normal script before we can use them, and some are actually only valid in REPL mode, like the underscore, for example. Two of the most important things that are available on the global object in a normal script are the process object and the buffer object. Let's talk about those first. The node process object provides a bridge between a node application and its running environment. It has many useful properties. Let's explore some of them. We can use process.versions to read versions of the current node and its dependencies. We can use these versions numbers to determine if we should run some custom code. For example, maybe for an older version of V8. One of the most useful properties on the process object is the env property. The env property exposes a copy of the user environment, which is the list of strings you get with the env command in Linux machines and the set command in Windows. The word copy here is key. If we modify process.env, which we can actually do, we won't be modifying the actual user environment, so keep that in mind. You should actually not read from process.env directly. We usually use configuration variables like password or API keys from the environment. Also, which ports to listen to, which database URIs to connect to. You should put all of these behind the configuration or settings module and always read from that module, not process.env directly. This way, if you decide to change the way you read these configurations, you modify one module. Here's a new and interesting property, process.release.lts. This will have the LTS label of the used node release, and it will be undefined if the currently used node release is not LTS. So we can check this label and maybe show a warning if an application is being started in production on a non-LTS node. The most useful thing we can do with the process object, though, is to communicate with the environment, and for that we use the standard streams, stdin for read, stdout for write, and stderror to write any errors. Those are pre-established ready streams, and we can't actually close them. We're going to talk about streams in details in Module 7 of this course. The process object is an instance of event emitter. This means we can emit events from process, and we can listen to certain events on the process. We're covering event emitters in Module 3 of this course, but let me show you one quick handy event that you should definitely be aware of. onExit is emitted when node's event loop has nothing else to do, or when a manual call to process.exit has been executed. We can't stop the node process from exiting here, but maybe we can log this somewhere or send an alert that this particular process is gone and maybe someone should do something about it. However, we can only do synchronous operations inside this event handler. We can't use the event loop here. One other usually misused event on the process is the uncaught exception event, which is emitted whenever a JavaScript exception is not handled, and it bubbles all the way to the event loop. In that case, and by default, Node will print the stack trace and exit. Unlike the exit event though, if we register a handler on the uncaught exception, Node will not exit. And this is bad and unpredictable in some cases. So you should avoid doing this interrupt and let the process exit. You can use another monitor process to restart the exiting process if needed. Here's an example to show the difference between exit and uncaught exception. Let's register handlers for both events. We can use process.stdn.resume to keep the event loop busy because otherwise Node will exit anyway. Then let's trigger a type error exception by calling an undefined method on console. If we only had the process event handler, the script will report the exit code and actually exit. But since we registered the handler for the uncaught exception event and did not manually exit the process, Node will keep running, often in an unpredictable state. The safest option here is to let the process exit anyway. When you get an uncaught exception, your code has a problem that needs to be fixed, so not letting the process exit might actually do a lot more damage. When the process exits, the exit event handler will be invoked. The buffer class, also available on the global object, is used heavily in Node to work with binary streams of data. A buffer is essentially a chunk of memory allocated outside of the V8 heap, and we can put some data in that memory, and that data can be interpreted in one of many ways depending on the length of a character, for example. That's why when there is a buffer, there is a character encoding, because whatever we place in a buffer does not have any character encoding. So to read it, we need to specify an encoding. When we read content from files or sockets, if we don't specify an encoding, we get back a buffer object. So a buffer is a lower level data structure to represent a sequence of binary data, and unlike arrays, once a buffer is allocated, it cannot be resized. We can create a buffer in one of three major ways. Allocate, create a filled buffer of certain size, while allocate unsafe will not fill the created buffer. So that might contain old or sensitive data and need to be filled right away. To fill a buffer, we can use the buffer.fill. Let's have some fun with allocate unsafe. This command allocates an 800 bytes buffer without initializing it. So if we try to read its content, we'll actually see some data. In fact, we might see things that we can recognize. If we keep trying, we might actually access previous things that we use the memory for. So while allocate unsafe has clear performance advantages, be careful with it. We can also create a buffer using the from method, which accepts a few different types in its argument. Here's an example to understand the difference between buffered data and normal data. Using the same UTF-8 string, when we put it in a buffer, the buffer does not have a character encoding, so it will represent the special character with its internal UTF-8 representation and returns the actual number of bytes used, while the string is counting characters based on the default UTF-8 encoding. Buffers are useful when we need to read things like an image file from a TCP stream or compressed file or any other form of binary data access. Just like arrays and strings, on buffers, we can use operations like includes, indexOf, and slice, but there are some differences with these methods when we use them on buffers. For example, when we do a slice operation on a buffer, the sliced buffer shares the same memory with the original buffer. In this example, we have a conversion map. We want to process a file and convert the last 3 bytes of the file according to the map, working with binary data directly. We read the file into a buffer, slice the buffer to get another binary buffer that holds only the last 3 bytes. Loop over this small buffer to do the conversion. Once done, Not only the sliced buffer has changed, but the original buffer is changed too because they share the same memory space. One final note on buffers. When converting streams of binary data, we should use the string decoder module because it handles multi-byte characters much better, especially incomplete multi-byte characters. The string decoder preserves the incomplete encoded characters internally until it's complete and then returns the result. The default two-string operation on the buffer does not do that. Let me explain this with an example. Say we have a binary input coming from somewhere and we want to encode it into UTF-8 characters. We're receiving this input incrementally. For a simulation, I'll type bytes into the standard int stream and this code will read what it gets, puts it in a buffer, and then tries to print it with both toString method and the string decoder .write method. Very simple. Now I'm going to feed the script 3 UTF-8 encoded bytes which represent the euro symbol. But you'll notice after every input, toString method is clueless, while the string decoder is smartly trying to make sense of the input. When it discovers that what we entered so far is actually a euro symbol, it outputs that. So in general, if you're receiving UTF-8 bytes as chunks in a stream, you should always use string decoder. Modularity is a first-class concept in Node, and fully understanding how it works is a must. There are two core modules involved. The require function, which is available on the global object, but each module gets its own require function, and the module, also available on the global object, and is used to manage all the modules we require with the require function. Requiring a module in Node is a very simple concept. To execute a require call, Node goes through the following sequence of steps. Resolving, to find the absolute file path of a module. Loading is determined by the content of the file at the resolved path. Wrapping is what gives every module its private scope and what makes require local to every module. Evaluating is what the VM eventually does with the code. And then caching so that when we require this module again, we don't go over all the steps again. We'll talk about every step in more detail in this clip. Have you met the module object? It has some interesting properties. First, an ID to identify it. The full path to the module file is usually used here, except for this root module. A dot is used instead. The path to the file name can be accessed with the file name property. Node modules have a one-to-one relation with files on the file system. We require a module by loading the content of a file into memory. However, before we can load the content of a file into the memory, we need to find the location of the file. For example, if we require a findme module from the index module, Node will look for findme.js in these paths, which start from the current directory and go up all the way to the root directory. If it can't find findme.js in any of these paths, it will throw a cannot find module error. To be exact, Node will actually look for the findme.js in more folders, but those are supported for mostly historic reasons and using them is no longer recommended. Also, core Node modules are an exception here. The resolve step returns immediately for core modules. Let's see how Node actually resolves a non-core module. We'll use the first path here, a Node modules directory under the current directory. We'll create one manually and simply add a findme.js file in there. Let's also add a console log line here in this file to identify it, and we'll do the same for index.js. When we now execute the index file, Node will find a path to findme.js and it will load it. If we want to only resolve the module and not execute it, we can use require.resolve method. This behaves exactly the same as require, but does not load the file. It will still throw an error if the file does not exist. This can be used, for example, to check whether an optional package is installed or not. If another findme.js now existed in any of the other paths, for example, if we have a Node modules directory under the home directory, and if we have a different findme.js file in there, I'm going to put a different console.log line in there, and I'm going to change this back to require. Now, if we execute the index file, the findme.js file in this new root node modules directory will not be loaded because Node already resolved findme.js to the local file found under the local node modules directory. But if we remove the local file and execute again, Node will actually just pick the next closest findme.js, and that would be the one under the home directory node modules directory. Modules don't have to be files. We can also create a findme folder under node modules and place an index.js file in there. We'll do a console log line here also to identify it. And now when we execute node index.js, it will actually load the index file under node modules. Index is the default file name, but we can control what file name to start with under the folder using the main property in package.json. For example, to make the required findme line resolve to this start.js file instead of index.js, we just need to add this package.json file, which says that when the findme folder gets required, start.js is the file that should be loaded. And let's test that. And now you can see how the require findme line actually loaded the start.js file and not the default index.js file. Other than resolving modules from within the node modules folder, we can also place the module anywhere we want and require it with either relative paths, dot and dot dot, or with absolute paths, starting with slash. If, for example, findme was under a lib folder instead of the node modules folder, we can still require it this way. Let me actually create a lib folder and put a findme.js file in there. Identify it with a console log statement, make sure things work. And to see the paths in action here, let's console log the module object. We'll also console log module from within the index file to see the difference, because those two module objects, which appear to be global, are actually different. Let's see that. First, the ID for the findme module is the full path. You'll also see that our main index.js module is now listed as the parent for our findme module. However, the findme module was not listed as a child of the index module. Instead, we have this weird circular thing going on because this is a circular reference. If Node prints the findme module object here, it will go into an infinite loop. That's why it simply replaces the findme content here with circular. More importantly now, what happens if the findme module required the main index module? This is where we get into what's known as the circular modular dependency, which is actually allowed in Node. To understand it better, let's first understand a few other concepts on the module object. First, let's talk about exports. In any module, exports is a special object. Anything we put on the exports object, we can see here, and it's actually what we get in the findme exports constant here. I'll console log this constant and put an ID attribute on the exports object in the findme module to identify it. When we test that, the findme exports constant has that ID attribute. Let's also talk about the loaded attribute here, which Node keeps false as long as there's still more content to be loaded. In our example, when we printed this line, Node was not done loading the modules and it printed loaded false for both. If we simply put all this code in an immediate timer to be executed in the next round of Node's event loop, then both modules will be labeled loaded true here, as at that point Node was done loading them. Notice how the findme constant did not get the exported values because this require line was done executing before the timer kicked in. We simply cannot use the exports object inside timers. Let's now try to answer the original question. What happens when module 1 requires module 2 and module 2 requires module 1? Let's find out. Let's create an M1 module under the lib folder. We'll require it in index.js and console log it. Under the lib folder, m1.js, let's give it an ID to identify it. And let's add some more content in here. We'll start an array with one value and then push two more values after that. And let's duplicate m1 as m2 and use different values in there. Now we'll make M1 require M2 somewhere before it's done loading. Now to the interesting point. If anywhere within M2 we required M1 and printed it, we have a circular reference. Node will partially print M1 here. At this point of the lifecycle of M2, the M1 module is not ready yet. It still has 2 more lines to be processed, but Node was able to share a partial exports object from M1 to M2. In terms of the loaded attribute, in this line in M2, the M1 module had a loaded false attribute, while in this line of the index file, the M1 module has the loaded true attribute. We can define and require JSON files and C++ add-on files with the node require function. The first thing Node will try to resolve is a .js file. If it can't find a .js file, it will try a .json file, and it will parse the file if found as a JSON text file. After that, it will try to find a binary .node file. Let's see examples for those extra extensions. If we have under node modules a data.json file, and we have some valid JSON data in there, then we can require data in here, and Node will parse the content of data.json into our data constant. This is useful when, for example, all you need to export is some static configuration data. You can simply put that in a config.json file and just require that. I like to always use an extension when I'm not requiring a .js file, just to make that signal clear in the code. But you should know that it will also work without an extension. If Node can't find a .js or a .json file, it will look for a .node file, and it would interpret the file as a compiled add-on module. Let's do a quick add-on example. The Node documentation site has a sample add-on file which is written in C++. It's a simple module that exposes a hello function, and the hello function outputs world. If we have a require add-on line like this, and we compiled this hello.cc file into add-on node, we can use the add-on node file directly here and use its hello method. To get this to work, we need to compile hello.cc first, which is simple. Create an add-on source directory and place hello.cc in there. And then on that same level, copy this build configuration into a binding.gyp file. This simply tells the compiler which file to compile and what target name to use for the compile module. Then to compile, we need the node gyp package. So install that, and once we have it, from within the add-on source folder, we run node gyp configure, which will create the make files under a build directory. We then run node gyp build, and that should create the binary compiled add-on.node file. This is the file that we can require. I'll copy it under the local node modules folder, and now our require script here should work. This is the output we've seen in the C++ code. We can actually see the support of these 3 extensions by looking at require.extensions. These are the actual functions that get executed. For example, for a .js file, Node just compiles the content, while for a .json, it uses json.parse on the content. For a .node file, it uses process.dlopen. Node's wrapping of modules is often misunderstood. To explain them, let me start by asking an important question. We can use the export object to export properties, but we cannot replace the export object directly. When we need to replace the export object, we need to use the module.exports syntax. The question is, why? Also, we've seen how the variables we define in the module scope here will not be available outside the module. Only the things that we export are available. So how come the variables are magically scoped and the exports object can't be replaced directly? The answer is simple. Before compiling a module, Node wraps the module code in a function, which we can inspect using the wrapper property of the module. This function has 5 arguments: exports, require, module, file name, and dir name. This function wrapping process is what keeps the top-level variables in any module scoped to that module. And it is what makes the module exports require variables appear to look global when in fact they are specific to each module. Same thing for the file name dir name variables, which will contain the module's absolute file name and directory path. All of these variables are simply function arguments whose values are provided to the wrapped function by Node. You can see this wrapping in action if you run a script with a problem on its first line. This might actually depend on your environment, but on mine you can clearly see the anonymous wrapping function and its arguments here. Since we are in a function, we can actually access the function's arguments in here. And you'll see how the first argument is the empty exports object, then we get the require object, then the module object, then file name and dir name. And note how both the require object and the module object are the copies associated with this index file. They are not global variables. The wrapping function's return value is this exports object reference. Note how we have both exports and the module object itself passed in the wrapper function. Exports is simply a variable reference to module.exports. So what happens here is equivalent to doing this line at the top of the module. So we can change the properties of the exports object, but if we change the whole export object, it would no longer be a reference to module.exports. This is the way JavaScript reference objects work everywhere, not just in this context. There's nothing special about require. It's a function that takes a module name or path and returns the exports object. We can simply override the require function to do our own logic if we want to. Say, for example, for testing purposes, we want every require line to be mocked by default and just returns an empty object instead of the required module exports object. This simple reassignment of require will do the trick. And if we test that by requiring any module and console logging that module, we'll get the mocked object by default. To explore this require object a bit more, let's say we have this simple print function. It takes a numeric argument stars and a string argument header, and it prints this header between the number of stars that we specify. And we want to use this file in two ways. We want to use it on the command line, just like this, by passing the stars and the header arguments as command line arguments. But we also want to use it with require. We just require the file and then use whatever the file exports as a function and call that function. So those are two different usages here. And we need a way to determine if the file is being run as a script or if the file is being required. This is where we can use this simple if statement. If require.main equal the module object. When we run this as a script, this if statement will be true. So we can simply call the function here with process argv elements. Otherwise, if require.main does not equal module, it means that this file is being required by other files. And in this case, we can just change the exports object to be the print function. And now we can test this script. It should work both from the command line directly and when we run the index file, which requires the print stars. Caching is important to understand. Here's a simple example to demonstrate it. Say that we have this ASCII art file that prints a cool looking header, and we want to display this header every time we require the file. So if we require this line twice, we want the header to show up twice. But because of modules caching, that's not going to happen. Node caches the first call and does not load the file on the second call. We can see this cache using require.cache, and in there you will find an entry for the ASCII art file. Those entries are indexed by the full file path. We can actually remove the cache entry here if we want to, using this full file path, and Node will reload the module fine after that. But this is not the most efficient solution for this problem. The simple solution for this case is to wrap the log line here in a function and exports that instead. Then when we require the file, we just execute the exports object as a function, and every time we do so, the function will execute the console log statement. NPM has a lot to offer. I want to make sure that you know all the great things you can do with NPM. NPM is not really part of Node. It just comes packaged with Node since it's the default and most popular package manager. It's also certainly not the only package manager. Recently, Facebook released another package manager, Yarn, which claims to be a lot faster than NPM, and if you compare them in the same project, that claim is probably true. But when we talk about NPM, there are two different things here: the NPM CLI and the NPM registry at npmjs.com. They work together out of the box. But the NPM CLI can actually work with different registries. It can be used with local files, folders, and private registries, and it can even be used with Git repositories directly. For example, to install the Express package directly from GitHub, we can do npm install express.js, which is the name of the GitHub organization hosting the Express project, and Express is the name of the repo, and this will install Express from the last commit on the master branch of the GitHub repo. We can see that with npm ls express. When you have a package installed from GitHub, the npm ls command will show the head commit for that install. We can also install a GitHub repo package from a specific commit or tag branch. For example, to install Express version 4.14.0 directly from GitHub, we can do something like #4.14.0. This works with branches and direct commit hashes as well. So you have a lot of flexibility in installing the package at specific points in its history, which is helpful in many ways. If you want to check what package a command will install without actually installing them, you can use the --dry run argument, which will only report what will be installed. To see a list of all globally installed packages, we can use the command npm ls-g, but this by default will list all top-level packages and their dependencies, which is usually a big tree. To see only the top-level packages, we can control the depth of the tree with --depth equal 0. This shows only the first level of the tree. By the way, to see more information about installed packages, you can use the ll command instead of the ls. This shows the description and more information about every package. If you're reading the output of npm ls from a program and you want to parse it, you can use the --JSON argument to get the output in JSON. When we installed Express locally in this directory, a node modules folder was created. I'm going to remove this node modules folder, and I'll create a node modules folder in the home directory. I'll then install Express locally here. You'll notice that npm used the home node modules folder and did not create a local one. Maybe you do need a single place to install all local dependencies, but this is usually a bad practice. The recommended way is to have a package.json file on this level, which instructs npm to manage the dependencies in a local node modules folder. The bare minimum package.json file should have a name. This name is a one word without spaces, and it should all be lowercase, and a version, which should follow the semantic versioning style. First number is the major version, second is minor, and third is patch. Once we have a package.json, npm install express will create a local node modules folder, even if a parent folder also have it. Using npm install directly like this is not recommended. If you're installing a dependency, you should document it in package.json. You can document it under three main categories. If you use npm --save or the shortcut -S, the dependency will be considered a production dependency. Let's install request as a production dependency. If you use --save dev or D for short, the dependency will be considered a development dependency. Let's install Babel CLI as a development dependency. If you use --save optional or O for short, it will be considered an optional dependency. You can use this for a recommended tool that's not required. For example, let's install nodemon as an optional dependency. For optional dependencies, the code should usually check for their existence and only use them if they're installed. After all these commands, take a look at package.json and see how these dependencies are documented under the three different categories. You can use the npm update command to update either a single package or all installed packages when the package name is not provided. When there is a version range specified in package.json, the update command will work according to that. A version range is composed of an operator and a version. Operators like less than or equal, or just equal. The equal operator is actually the default operator if no operator was specified. An X or a star can be used in one of the three semantic versioning numbers to cover the whole range for that level. This has the same effect as not specifying that same level. Other operators include the tilde, which works just like an X in the last level, but only when the X is greater than what's specified. So if we have 1.2.3 in here, this version range is equivalent to 1.2.x, but only for all x greater than or equal to 3. And this version range is equivalent to 1.2.x for all x greater than or equal to 0. There's also the caret operator, which works well for packages with versions less than 1.0 because it only allows changes that do not modify the leftmost non-zero digit in the semver array. To update the npm CLI itself using npm, you can do npm install npm-g, and this will update npm itself. To check to see if any of the installed packages are outdated, we can use the npm outdated command. This works globally too. npm has a lot of configurations that we can control. We can see a list of all the configurations we can control with npm config list-l. For example, if you use npm init a lot, you might want to change the default values that it uses by changing the init configurations. For example, to set the default value for the package author's name, you can use a command like this one. Now we have a default value for the author name. And to delete that, you can use npm config delete. Another very useful configuration to have set is the save true configuration. This will make install always use the --save flag, which I think is great. We can search the npm registry using the search command right from the command line. Let me look for packages that has the word lint in them. And there is a lot of them. So you can grep this list and see which one you're looking for. The npm shrinkwrap command can be used to lock down all the dependency versions, so every time anyone runs the npm install command, they get the exact same versions for all the packages. And before we conclude, here are some of my favorite npm tricks. The npm home command can be used to open the home page of a package. How cool is that? There's also npm repo, which will open the repository page of a package. If you have packages installed in Node modules, but are not saved to package.json, for example, I think Express was installed without saving it to package.json. So if we want to clean that up, we can use the npm prune command. So I think this removed Express and its dependencies. And finally, npm has some Easter eggs. My favorite is the Christmas Easter egg. In this module, we've first seen an overview of the full course, then started talking about Node's architecture and how Node interacts with V8 and libuv. We've seen the different ways to use the Node command and its REPL mode, covering some tips and tricks to use and customize the REPL mode, and a few of the useful command line options we can use with the Node command. Then we talked about the global object and what's available on it by default, and covered the process object and how it's a bridge between a Node's process and its running environment. We also talked about the buffer module and its role in Node applications, and also saw an example of using the string decoder module. We then learned about the require module and its 5 different steps. We first explored the module object, which is used to manage required modules, and then learned about the resolving steps and the various ways a required module can be resolved. We also learned about what happens when 2 modules require each other. We then learned how the require function supports loading JSON files and C++ add-on files, and compiled and built a simple C++ add-on module with the use of the Node GYP package. We also talked about the wrapping and caching of required modules and explained how Node wraps every module with a function that it uses to control some global arguments. We also talked about how the required function caches every module it loads and how to work around that if we need the code to be re-executed every time we require it. And finally, we talked about npm and its main commands and configurations and a few tips and tricks when working with it. In the next module, we'll talk about Node's concurrency non-blocking model and take a look at how the event loop works. One of the most important concepts to understand about Node.js is its concurrency model for handling multiple connections and the use of callbacks. You might know this as the non-blocking nature of Node.js. In Node, this model is based on an event model, just like Ruby's event machine or Python's twisted. In Node, this event model is organized through what's known as the event loop. Slow I/O operations are handled with events and callbacks so that they don't block the main single-threaded execution runtime. Everything in Node depends on this concept, so it's extremely important that you fully understand it. Okay, so we know that I/O is short for input-output, but what exactly does that mean? I/O is used to label a communication between a process in a computer CPU and anything external to that CPU, including memory, disk, network, and even another process. The process communicates with these external things with signals or messages. Those signals are input when they are received by the process and output when they are sent out by the process. The term I/O is really overused because naturally, almost every operation that happens inside and outside computers is an I/O operation. But when talking about Node's architecture, the term I/O is usually used to reference accessing disk and network resources, which is the most time-expensive part of all operations. Node's event loop is designed around the major fact that the largest waste in computer programming comes from waiting on such I/O operations to complete. We can handle requests for these slow operations in one of many ways. We can just execute things synchronously. This is the easiest way to go about it, but it's horrible because one request is going to hold up other requests. We can fork a new process from the OS to handle each request, but that probably won't scale very well with a lot of requests. The most popular method for handling these requests is threads. We can start a new thread to handle each request. But threaded programming can get very complicated when threads start accessing shared resources. A lot of popular libraries and frameworks use threads. For example, Apache is multi-threaded and it usually creates a thread per request. On the other hand, its major alternative, Nginx, is single-threaded, just like Node, which eliminates the overhead created by these multiple threads and simplify coding for shared resources. Single-threaded frameworks like Node use an event loop to handle requests for slow I/O operations without blocking the main execution runtime. This is the most important concept to understand about Node. So, how exactly does this event loop work? Let's find out. The simplest one-line definition of the event loop is this. It's the entity that handles external events and converts them into callback invocations. Helpful? Maybe not. Let's try another definition. It's the loop that picks events from the event queue and pushes their callbacks to the call stack. This one is probably worse than the first one. Truth is, it's not easy to understand the event loop without first understanding the data structures it has to deal with. It's also a lot easier to understand the event loop with visuals rather than text. So the next few clips will explain the various things around the event loop with visuals. What I want you to understand first is that there is this thing called the event loop that Node automatically starts when it executes a script, so there's no need for us to manually start it. This event loop is what makes the asynchronous callback programming style possible. Node will actually exit this event loop when there are no more callbacks to perform. The event loop is also present in browsers, and it's very similar to the one that fires in Node. To understand the event loop, we need to understand all the players in this diagram, and we need to understand how they interact. So V8 has this thing called stack, which we're going to cover in detail in the next clip. It also has a heap. The heap is simple. It's where objects are stored in memory. It's basically the memory that gets allocated by the VM for various tasks. For example, when we invoke a function, an area in this heap is allocated to act as the local scope of that function. Both the stack and the heap are part of the runtime engine, not Node itself. Node adds APIs like timers, emitters, and wrappers around OS operations. It also provides the event queue and the event loop using the libuv library. The event loop, as the name clearly describes, is a simple loop that works between the event queue and the call stack. But again, we can't understand it without first understanding those other entities. The V8 call stack is simply a list of functions. A stack is a first in, last out simple data structure. The top element that we can pop out of the stack is the last element that we pushed into it. In the case of V8 call stack, these elements are functions. Since JavaScript is single-threaded, there's only one stack and it can do one thing at a time. If the stack is executing something, nothing else will happen in that single thread. When we call multiple functions that call each other, we naturally form a stack. Then we backtrack the function invocations all the way back to the first caller. Remember how if you want to implement something that's recursive without recursion, you need to use a stack? Well, that's because a normal recursive function will use a stack anyway. Let's walk through a simple example to demonstrate what happens in the stack when we call functions. Here we have three simple functions: add, double, which calls add, and print double, which calls double. And let's assume that all these functions are wrapped in an immediately invoked function expression. When we run this code, V8 uses the stack to record where in the program it is currently executing. Every time we step into a function, it gets pushed to the stack. And every time we return from a function, it gets popped out of the stack. It's really that simple. So we start with the ify call, which is an anonymous function. Push that to the stack. The ify function defines other functions, but only executes print double. That gets pushed to the stack. Print double calls double, so we push double to the stack. Double calls add, we push add to the stack. And so far, we're still executing all functions. We have not returned from any of them. When we return from add, we pop add out of the stack. We're done with it. Then we return from double. So double gets popped out of the stack too. Now the execution continues in print double. We get into a new function call, console log. That gets pushed into the stack and popped immediately because it did not call any other functions. Then we implicitly return from print double. So we pop print double out of the stack and finally pop the anonymous ify itself out of the stack. Note how every time a function is added to the stack, its arguments and local variables are added to in that same level. You'll sometimes hear the term stack frame to reference the function and its arguments and local variables. I am pretty sure you have seen the call stack before. If not in Node, then in the browser. Every time you get an error, the console will show the call stack. For example, I changed add to use an undefined variable here, which will raise an error. When we execute this code in Node or the browser, we'll get an error report which includes the call stack. The anonymous function calls print double, which calls add. This is the state of the call stack when the error happened. And what do you think will happen if a function calls itself recursively without an exit condition? It's the equivalent of an infinite loop, but on the stack. We'll keep pushing the same function to the stack until we reach the V8 size limit for the stack. And V8 will error out with this error, maximum call stack size exceeded. As long as the operations we execute in the call stack are fast, there is no problem with having a single thread. But when we start dealing with slow operations, the fact that we have a single thread becomes a problem because these slow operations will block the execution. Let me simulate that for you with an example. You do know that we can still write blocking code in Node, right? For example, a long for loop is a blocking operation. In here, the slow add function will take a few seconds to complete, depending on the hardware, of course. So what happens in the call stack when we step into a blocking function like slow add? Well, the first time we step into it, it gets pushed to the stack. And then we wait until V8 finishes that useless blocking loop and returns from slow add 3.3, which gets popped out of the stack at that point. Then we step into slow add 4.4 and we wait, done, return, pop. Same thing for slow add 5.5, wait, done, return, pop. Then we get into the console log lines, which are fast and thus non-blocking. So push, pop, push, and pop. Let me actually show you how Node behaves when we execute this exact code. Slow add, wait, slow add, wait, slow add, wait, print, print, print. While Node is waiting after every slow add here, it cannot do anything else. This is blocking programming, and Node's event loop exists to allow us to avoid doing this style of programming. We all know that Node API is designed around callbacks. We pass functions to other functions as arguments, and those argument functions get executed at a later time somehow. For example, if we change our slow add function to output the result in a set timeout call after 5 seconds, the first argument to set timeout is the function that is famously known as a callback. So let's see what happens on the stack for this case. We call slow add 3 and 3, push that to the stack. Slow add calls set timeout, so we push that to the stack. Since set timeout does not call any functions but rather has a function argument, it gets popped out of the stack immediately, and at that point slow add 3 and 3 is done, so we pop that out of the stack too. Then we continue. Slow add 4 and 4, push it to the stack, calls set timeout, push that to the stack and immediately pop it, then pop slow add 4 and 4, then somehow console log 6 gets added to the stack to be executed, and after that console.log 8 gets added to the stack to be executed. To understand how the last two calls to console log appeared in the call stack, let's take a look at the bigger picture here. First, it's important to understand that an API call like setTimeout is not part of V8. It's provided by Node itself, just like it's provided by browsers too. It's wired in a way to work with the event loop asynchronously. That's why it behaves a bit weirdly on the normal call stack. Let's talk about the event queue, which is sometimes called the message queue or the callback queue. It's simply a list of things to be processed. Let's call these things events. When we store an event on the queue, we sometimes store a plain old function with it. This function is what we know as a callback. A queue data structure is a first in, first out structure. So the first event we queue will be the first event to get dequeued. To dequeue and process an event from the edge of the queue, we just invoke the function associated with it. Invoking a function will push it to the stack. So we start with the anonymous function. It pushes slow add 3 to the call stack, which in turn pushes set timeout callback 1 delay of 5 seconds. The set timeout callbacks here in this example are actually anonymous functions, but to simplify the visualization, I labeled them callback 1 and callback 2. At this point, Node sees a call to its setTimeout API, takes note of it, and instantiate a timer outside of the JavaScript runtime. The setTimeout call on the stack will be done and popped out. And while the Node timer is running, the stack is free to continue processing its items. It pops slow add 3, pushes slow add 4, which in turn pushes setTimeout with the second callback. Node kicks off another timer for this new setTimeout call, and the stack continues to pop its done functions. After 5 seconds, both timers complete, and when they do, they queue the callbacks associated with them into the event queue. Exactly at this moment, the event loop has something important to do. The event loop job is super simple. It monitors the call stack and the event queue. When the stack is empty and the queue is not empty, there are events waiting to be processed in the queue, it will dequeue one event from the queue and push its callback to the stack. It's called an event loop because it loops this simple logic until the event queue is empty. Right now, our example's call stack is empty, and the queue is not. The event loop will pick callback 1 and push it to the stack. Callback 1 will push console log call to the stack, which returns immediately, and this marks callback 1 as done. The stack is empty again, and we still have one event to process, so the event loop will push callback 2 to the stack. And callback 2 pushes console log, done, pop, callback 2 is done. And we are at an idle state now for the event loop. The stack is empty and the queue is empty. Node will exit the process when we reach this state. All Node APIs work with this concept. Some process will go handle a certain I/O asynchronously, keeping track of a callback, and when it's done, it will queue the callback into the event queue. Keep in mind that any slow code being executed on the stack directly will block the event loop. Similarly, if we're not careful about the amount of events that get queued in the event queue, we can overwhelm the queue and keep both the event loop and the call stack busy. As a Node developer, these are some of the most important things to understand about blocking versus non-blocking code. What happens when the timer delay is 0 milliseconds? Well, almost the same thing. Let's walk through it. The main function pushes slow add 3 and 3, which pushes the set timeout, which creates the timer. The timer immediately queues its callback on the queue. However, the event loop will not process that event because the stack is not empty. So the stack continues its normal flow until we get to the second timer, which also immediately queues its callback. The stack is still not empty. After we pop all calls from the stack, the event loop picks the first callback and pushes that to the stack, and then does the same thing with the second one. Because of this loop, the timers are not really executed after 0 milliseconds, but rather after we're done with the stack. So if there was a slow operation on the stack, those timers will have to wait. The delay we define in a timer is not a guaranteed time to execution, but rather a minimum time to execution. The timer will execute after a minimum of this delay. Node's event loop has multiple phases. The timers run in one of those phases, while most I/O operations run in another phase. Node has a special timer, set immediate, which runs in a separate phase of the event loop. It's mostly equivalent to a 0 millisecond timer, except in some situations, set immediate will actually take precedence over previously defined 0 milliseconds set timeouts. For example, this code will always display immediate before timeout, although we kick the 0 millisecond timeout first. It's generally recommended to always use set immediate when you want something to get executed on the next tick of the event loop. Ironically, Node has a process.nextTick API that is very similar to setImmediate, but Node actually does not execute its callback on the next tick of the event loop. So the name here is misleading, but it's unlikely to change. Process.nextTick is not technically part of the event loop, and it does not care about the phases of the event loop. Node processes the callbacks registered with next tick after the current operation completes and before the event loop continues. This is both useful and dangerous, so be careful about it, especially when using process.nextTick recursively. One good example for using nextTick is to make for a standard function contract. For example, in this script, the file size function receives a file name argument and a callback. It first makes sure the file name argument is a string, and it executes the callback with an error if not. Then it executes the async function fstat and executes the callback with the file size. An example use of the file size function is here where we log the file size. Very simple. If we execute it with the current file name, it should log the size of the file. This call was async because we saw the hello message first, which is expected because of our use of the async fstat function. But something is wrong with the file size function. Can you identify it? Let me give you a hint. Let's trigger the validation by passing a number instead of a string here. Validation is a go, but the console hello line was not executed at all in this case because the validation code here is synchronous. So the file size function could be both sync and async depending on the first argument. This is usually a bad design. A function should always be either sync or async. To fix this problem, instead of directly calling the callback with an error here, we can use process.nextTick call for the callback and with the argument of the error that we want. This way, when we actually trigger the validation, the error will happen asynchronously, and the file size function is going to be always async. I hope this module helped you understand Node's event loop and its event-based concurrency model. We looked at V8's call stack and how that is a record of where in the code V8 is currently executing. We looked at how slow operations affect the single-threaded call stack and looked at Node APIs like setTimeout, which does not really run at V8, but rather as a Node API that does not block the call stack. Node pushes asynchronous operations as events to its event queue, and the event loop monitors both the call stack and the event queue and dequeue callbacks from the event queue into the call stack, which gives V8 back the control to execute the content of those callbacks. We've also looked at two special API calls: setImmediate, which is similar to a 0-millisecond timer, and process.nextTick, which pushes a callback immediately after the current operation and before the event loop continues. In the next module, we'll dive deeper into Node's event-driven architecture and see how events and listeners work with the event loop and how to use Node's event emitter class. The original way Node handled asynchronous calls is with callbacks. This was a long time ago, before JavaScript had native promises support and the async await feature. We saw how asynchronous callbacks work with the event loop, but callbacks in the general definition are just functions that you pass to other functions, which of course is possible in JavaScript because functions are first-class objects. It's important to understand here that callbacks do not indicate an asynchronous call in the code. In Module 2, we saw how a function can call the callback both synchronously and asynchronously, and talked about how to avoid doing that with process.nextTick. Let's see an example of a typical asynchronous node function that's written with a callback style. ReadFile as array takes a file path and a callback, read the file, split the lines into an array of strings, and call the callback with that array. Here's an example used for it. We use it for a file that has only numbers, parse the array of strings to numbers, and count the odd ones. Just one simple example of using readFile as array. Note callback style is used purely here. The callback has an error first argument that's nullable, and we pass the callback as the last argument for the host function. Always do that in your functions because Node users will always assume that. So don't pass the callback argument first here, or flip error and lines here. In modern JavaScript, we have promise objects. Promises can be an alternative to callbacks for asynchronous APIs. Instead of passing a callback as an argument and handling the error in the same place, a promise object allows us to handle success and error cases separately, and also allow us to chain multiple asynchronous calls instead of nesting them. Let's convert this callback example to use promises. Instead of passing a callback as the last argument to readFile as array, we do a .then call on it. This .then will give us access to the lines array, and we can do our processing on it as before inside the .then call. And to handle the error, we do a catch call on the result to log the error. To convert the host function definition to work with this code, we start by returning a promise object, which wraps the fs readFile async call. The promise object exposes two functions, a resolve and a reject. We replace the error callback with a reject call, and replace the success callback with a resolve call. We're simply replacing callback calls with promise calls, and this callback argument is no longer used. This will work exactly the same. Although this code is a little bit easier to understand and work with, Node official method for working with asynchronous code is callbacks, and developers using your code might assume that you have a callback interface. If you want to work with promises, you can keep the callback mechanism and add a promise interface to it. Lots of popular Node packages started doing that. It's very simple. Don't replace the callback calls. Keep them and add a promise call. So we reject here the error and also return the callback with the error. And in here, we resolve with the lines and keep the callback invocation with the lines. The only other thing you need to do in this case is to have a default value for this callback argument in case the code is being used with the promise interface. We can use a simple default empty function in the argument here. Now this code will work both ways, with callbacks and with promises. Adding a promise interface makes your code a lot easier to work with when there is a need to loop over an async function. With callbacks, things become messy. Promises improve that a little bit, and function generators improve on that a little bit more. But a more recent alternative to working with async code is to use the async function, which allows us to treat async code as if it was linear, making it a lot more readable when we need to process things in loops. In my current Node version, this feature is behind a Harmony flag, but it will be officially available soon. To consume our readFile as array method with async await, we first create an async function, which is just a normal function with the word async before it. Inside the async function, we call the readFile as array function as if it returns the lines variable. And to make that work, we use the keyword await. After that, we continue the code as if the readFile as array call was synchronous. And to get things to run, we execute the async function. Very simple and more readable. However, to work with errors, we also need to wrap everything in a try-catch call like this, so don't forget that. To execute all this code, I currently need to run the file with the --harmony async await flag. and the read file as array function example will work as expected. It's actually now working with all three methods. It exposes both a callback interface and a promise interface, and we can consume it using callbacks, promises, and with the new async await feature in JavaScript. The event emitter is a module that facilitates communication between objects in Node. Event emitter is at the core of Node asynchronous event-driven architecture. Many of Node's built-in modules inherit from event emitter. The concept is simple. Emitter objects emit named events that cause listeners to be called. So an emitter object has two main features: emitting named events and registering listener functions. To work with event emitter, we just create a class that extends event emitter. Emitter objects are what we instantiate from event emitter based classes. At any point in their lifecycle, we can use the emit function to emit any named event we want. Emitting an event is the signal that some condition has occurred. This condition is usually about a state change in the emitting object. We can add listener functions using the on method, and those listener functions will simply be executed every time the emitter object emits their associated named event. Let's take a look at an example. Class withLog is an event emitter. It defines one instance function execute. Execute receives a task function and wrap its execution with log statements. It fires events before and after the execution. To see the sequence of what will happen here, we register listeners on both named events and actually execute a sample task here. What I want you to notice about the output here is that it all happens synchronously. There's nothing async about this code. We get the before executing line first, the begin named event causes the about to execute log line, then we execute, the end named event causes the done with execute line, and then we get the after execute line. So just like plain old callbacks, do not assume that events mean synchronous or asynchronous code. This is important because say that the execute task function was actually async. We can simulate that with a set timeout call here instead of a direct function. Now, this line will be async, and the two lines after it are not accurate anymore. To emit an event after an asynchronous function is done, we'll probably need to combine callbacks or promises with this event-based communication. One benefit for using events instead of regular callbacks is that we can react to the same signal multiple times by defining multiple listeners. To accomplish the same with callbacks, we have to write more logic for this inside the single available callback. Events are a great way for applications to allow multiple external plugins to build functionality on top of the application's core. You can think of them as hook points to allow for customizing the story around a state change. Let's convert this synchronous sample example into something asynchronous and a little bit more useful. The withTime class executes an async function and reports the time that's taken by that async function using console.time and console.timeEnd calls. It emits the right sequence of events before and after the execution, and also emits error data events to work with the usual signal of asynchronous callback. We call it simply by flattening the arguments of an async method, and instead of handling data with callbacks, we can listen to the data event now. When we execute this code now, we get the right sequence of events as expected, and we get a reported time for the execution, which is helpful. In the previous Clips example, there were two events that were emitted with extra arguments. The error event is emitted with an error object, and the data event is emitted with a data object. We can use as many arguments as we want after the named event, and all these arguments will be available inside the listener functions. For example, to work with this data event, the listener function that we register will get access to the data argument that was passed to the emitted event. And that data is exactly what the read file callback exposes. The other special event was the error event. The error event is a special one because if we don't handle it with a listener, the node process will actually exit. Let me show you what I mean. If we have two calls to the execute method, and the first call is triggering an error, the node process is going to crash and exit. To prevent this behavior, we need to register a listener for the special error event. And if we do so, that error will be reported and both lines will be executed. So the node process did not crash and exit in that case. The other way to handle exceptions from emitted errors is to register a listener for the uncaught exception process event. This will essentially be the same, but remember the advice that on uncaught exception, we should just let the process exit anyway. So usually when you use the uncaught exception, we'll do some kind of cleanup and then we'll have the process exit. However, imagine that multiple error events happened. This means the uncaught exception listener will be triggered multiple times, which might be a problem for any cleanup code we're doing here. The event emitter module exposes a once method instead of an on. This once method means invoke the listener just once, not every time it happens. So this is a practical use case to use with the uncaught exception, because on the first uncaught exception, we should start doing the cleanup and exit the process anyway. If we register multiple listeners for the same event, the invocation for those listeners will be in order. The first listener we register is the first listener that gets invoked. In here we have two listeners, and the length listener was invoked before the characters listeners. If you have a need to define a new listener but have that listener invoked first, you can use the prevent listener method. And if you need to remove a listener, you can use the remove listener method. Let's create a practical example using Node's event emitter. Let's create a simple task list manager. We'll keep the structure simple. We'll have a client file and a server file. The client emits a command event for the server, and the server emits a response event for the client. We'll make it support 4 commands: help to display the list of commands, ls to list the current tasks, add to add a new task, and delete to delete a task. To get started, I created a client.js file and a server.js file. We'll need to require the event emitter in both of them. In client.js, we need to read input from the user. For that, I'm going to use the readLine module. To use the readLine module, we create an interface with the input and output streams. And let's just use process standard in and process standard out. The client event emitter is going to be a simple one. There isn't a lot of logic in here. So instantiating an object directly from the event emitter should be okay. The server, on the other hand, is going to have some logic. So I'm going to create a class that extends event emitter, and I'll export an instance of that class. In the client file, we'll import this server object. However, since we're doing two-way communication here, the client and the server need access to each other. The client is going to emit events to the server, and the server is going to listen to those events. And the inverse is true as well. So in client.js, we have access to the server object because we just required it. We can do the same for the client, but another way we can do that is to make server.js exports a function and execute this function here with the client as an argument. So this allows us to go in server.js, and in here, assume that we have a function instead of just an object. This function is going to receive the client, and we can potentially instantiate the server object with the client object. So now in the server class, we can define the constructor function, and that constructor function is going to receive the client. Back in the client.js, let's go ahead and use the readLine interface. We can register a listener for the line event, which receives an input. So just to test that, let's go ahead and log this input line. We can test this with node client.js, and it's listening to the input and echoing it back. So now that we have access to input from the user, we can use the client to communicate this input to the server. So we can do client.emit the input, for example. Input is input. So now every time the user hits enter, the client is going to emit an input event to the server. So the idea here is to run this, we're going to do something like help here, and that would be the command for the server. In fact, let's name this event command instead of input to make it more clear. So to test all this, in server.js, let's go ahead and listen to any command event from the client. So on command, we're going to receive the command. We'll have a function here to do something with the command. I'm going to console log it for now, so we can test. Command is add. Perfect. So the commands that we want to implement are help, add, ls, and delete. Let's implement the first command. I'm going to create an instance method here for every command, and every one of them is going to emit a response named event. So for now, we'll do placeholders and copy help for add, ls, and delete. And to make sure we're only executing those supported commands, I'm going to do a switch statement here on the command. And inside here, I'll list all the supported commands. And for these supported commands, we're going to go ahead and execute them. So I'll pick the command and execute it. And for the default case, this would be an unknown command. So I'm going to go ahead and emit a response object here and say something like unknown command. So now inside the client file, we're emitting the command to the server, and the server is going to emit a response event. So what we need to do here now is to listen to that response event. So server on response, the listener here is going to be a function, and this function gets access to the response string. Let's just console log the response. So I think we can actually test all that. Help, add, delete, ls, and something unknown. Perfect. I'm going to do a trick here to make this more user-friendly. So basically we write this string, which is a special command that will clear the terminal. Then we write the response, and then we write a prompt to receive other commands. So now when we test this, it will be something like help, says help, and then receives another command, add, response with add, and it receives another command. So we should probably also do the same on the initialization of the server and instruct the user to type a command. Instead of doing it here manually, we can have the server respond with an initial response that says type a command. So that's exactly what I'm going to do. Right after we initialize, we're going to do this dot emit response, and in here say something like type command help to list all commands. However, this is not going to work for a very important reason. It's all about the sequence of what's happening. This line is going to be executed when we execute this line. So our handler for the response event would not be defined yet. To fix this problem, we can wrap this call in a process.next tick. So in here, we'll do process.next tick, have a function, and in this function, we'll do this .emit response, type a command, it's process.next tick. Let's test now. Things are working. Type a command, help to list command, help, add, an unknown command. Perfect. Now that we have the structure of this communication between the client and the server, implementing those commands are actually easy. The help command will just emit a string. Available commands are add, ls, or delete. The add command, on the other hand, is going to need to receive some arguments. We're going to say add something. So right now we don't have arguments. We're actually calling this with an empty argument. We're only receiving command here. So we can either process the command for its arguments in here or process it on the client side, which makes more sense to me. So I will initialize a command and arguments variables. Inside the line listener, I'm going to make the command and the rest of the arguments to be read from input when I split it on space. This way, the first token of this input is going to be the command, and the rest of the arguments will be in the args variable. So let's pass both the command and the args to the emitted event. Perfect. So now inside server.js, we will have access to a command and an array of arguments. And let's pass this array of arguments to every command we execute. So now we do have a list of arguments, so let's just test by responding with that list of arguments and joining it back with a string. So we can test that. If we do add hello there, it will display back hello there. Perfect. So the rest of the implementation here is purely JavaScript. So let me do it quick and fast forward, and let me review what I did. So I added a tasks object to hold the tasks information, a task ID to hold a unique counter for every new task. In the add method, we just add the new task to the tasks object, emit a response for the user that the task was added. For the delete method, we delete the task using whatever ID the user types in and give the user feedback that the task was deleted. And the ls method is going to use this new tasks string method to display the tasks. This is just a friendly output for the tasks object. We just loop over the keys, and for every key we return a string with the task information and then joining everything with a new line. So this is the final product. Let's go ahead and test it. Node client. We have a help command which lists all the available commands. Add task, ls, and delete. Let's add few tasks. Do this, add, do that. You'll see the feedback that tasks are added. We can list the tasks and we can delete a task. So let's delete one and list the tasks after that. We only have two. In this module, we explored the event-driven nature in Node using its core event emitter module. We first talked about the different ways we can deal with asynchronous code in JavaScript and how Node's standard way is to use an error-first callback as the last argument of an asynchronous function. We saw how we can combine callbacks with promises and how we can consume these promises using the new async await feature in JavaScript. We then learned about the event emitter module and saw how emitter objects emit named events that cause listeners to be called. We also saw how events can be used for both asynchronous and synchronous code. We saw how to use arguments with emitted events and how to handle the special error events and what happens when we register multiple listeners to the same event. We then created a practical example using Node's event emitter, which was a simple command-based task list manager with features to list, add, and delete tasks in a queue of tasks. In the next module, we'll explore Node's capabilities for working with TCP and UDP networking. Let's create a basic network server example. We use the nets module createServer method. We then register a connection handler that fires every time a client connects to this server. When that happens, let's console log the client is connected. The handler also gives us access to a connected socket itself. The socket object implements a duplex stream interface, which means that we can read and write to it. So let's write welcome new client. And to run the server, we need to listen to a port, and the callback here is just to confirm it. Let's test. Testing this is simple. We can use either telnet or netcat. For example, netcat localhost 8000, we get the client is connected message in the server console, and the welcome message is sent to the client. And then Node keeps running because we did not terminate that connection. Now the client can write to that socket, but we have not registered a handler to read from the socket. The socket being a duplex stream means that it's also an event emitter. So we can listen to data event on the socket. The handler for this event gives us access to a buffer object. Let's console log it. Now when the client types something, we get it as a buffer. This is great because Node does not assume anything about encoding. The user can be typing here in any language. Let's now echo this data object back to the user using socket.write. When we do so, you'll notice that the data we're writing back is actually a string. This is because the write method on the socket assumes a UTF-8 encoding here. This second argument can be used to control the encoding, and the default is UTF-8. We can also globally set the encoding if we need to. So the global encoding is now UTF-8, and the data argument here becomes a string instead of a buffer because we now told Node to assume a UTF-8 encoding for anything received from this socket. Both the console log line and the echoed data are assumed to be UTF-8. I'm going to keep the example without global encoding, just in case we need access to the buffer object. What happens when the client disconnects? The socket emitter has an on-end event that gets triggered when the client disconnects. At that point, we can't write to the socket anymore. Let's console log that client is disconnected. Let's test that now. Connect, and we can disconnect a netcat session with Control D. The server logs the line. Let's review what we did in the previous clip real quick. We created a network server using the nets module createServer method. This server object is an event emitter, and it emits a connection event every time a client connects to it. So we register the handler on this connection event. This handler gives us access to the connected socket. The connected socket is also an event emitter, and it emits a data event whenever the user types into that connection. And it also emits an end event if the user disconnects from that server. So now we have a server. We can connect to this server, type to it, and many users can connect to that server and also type to it. No problem there. They both can write to their sockets, and we can read from both sockets. These two connected clients get two different sockets. In fact, let's give every socket a unique ID. We can simply use a counter. I'm going to do counter, start from 0. Every time a client connects, we'll define an ID property for that socket and assign it the counter plus the counter for the next socket. And now on data, when we receive the data from the user, let's identify the socket. I'm going to remove this console log line here. We don't need it. And in here, instead of writing data as, I am going to write $variable socket.id to identify it. Just like that. So let's test one client, two clients. And now when this client types, it says 0. And when this client types, it says 1. So this makes the log clear. We have two different clients connecting here, and we can write to their sockets. To make these two clients chat with each other, all we need to do is, when we receive data from one of them, we write it to all the connected sockets. So we need to keep a record of all connected sockets and loop over them in the data event handler. We can use a simple object to keep a record of all connected sockets. Let's do that. Let's define a sockets variable and start it as an empty object. Every time a socket connects, let's store it in this sockets object. Let's index it with the ID that we just defined, just like that. Then on a data event, we can loop over this object. We can use object.entries, which is actually a new method in JavaScript, just like keys, but gives us both the key and the value. So entries for sockets dot for each, which give us a handler. Inside the for each handler argument, we can destructure both the key and the socket object, which I'm going to alias as client socket here, so that it doesn't conflict with the global socket that we're working with. And now inside the for each, we can just use our previous code to write to the socket. But instead of socket here, it's going to be CS, the socket that we have in the loop. And actually key is not used, so we can just remove it. We only care about the connected socket. And I do want to keep this as socket.id because that's the socket that's actually sending the data, so it's good to identify who is writing in that case. So let's test all that. Connect multiple clients and try typing in all of them. Hello? So you'll see how 0 said hello, 0 said hello in both of them. And then hi, you'll see how 1 said hi and 1 said hi in both of them. So let's review. On data from any socket, we loop over this sockets object and we write the received data to every socket in there. This is simply acting like a chat server because every connected client is receiving all the messages from every other connected client. However, if one client disconnects, our chat application will simply crash because now we're trying to write to a socket that was closed. So to fix that, in the end event here, when the socket emits an end event, we should delete it from the sockets object. So sockets for the socket.id. This would delete the disconnecting socket from the sockets object. In this way, if one client disconnects, the other client can still type and the server will not crash. So now we can say that we have a bare-bone chat server. We created a very basic chat server. So how about we improve it a little bit? Right now, we can run the server, clients can connect, we can identify them with their IDs, and they all receive all the messages. So usually when you chat, you don't really get echoed back your own messages. So let's have a condition here inside the for each to implement that. Basically, if the currently connected socket, which we can identify with socket.id, if that equals to the current socket, which is identified by the key, back to key here, if that condition is true, then the current socket in the loop is the same socket that is sending the data. So we should probably just return here and not write back to the user. So let's test that. So now when the first client types, client 1 and 2 both get the hello message, but client 0 does not get the hello message. Let's try hi in here. Client 0 and client 2 both get the message, but client 1 does not. Perfect. So how about we identify our chatters with names instead of numbers? Maybe we can ask them about their name when they first connect. So instead of this welcome new client message, I'm going to type, please type your name, just like that. And this means that the first data event I'll receive is going to be the name of the client. So I need a condition to identify if a client is just giving me their name for the first message, or is this a data event that's coming from a client who already gave me their name and they're just chatting now. So how about instead of adding every socket to the officially connected sockets, we make that a condition. We only add the socket when we receive the name of the user. So in here, we'll do a condition. We'll say if the socket is not part of the sockets connected, so if not sockets for the socket.id, then this means that we have not registered this socket yet, and this current data message is the name of the user. So we'll go ahead and register this socket now, and we'll store the name of the user, which is basically the data object. And remember that the data object is a buffer because we don't have a global encoding. So we'll do toString on it to convert it into UTF-8. And also we trim it to remove the new line. And in this case, we want to return. We don't want to echo this name back to all connected user because this is just a socket that's just connecting and giving me their name. How about we give the user a welcome message here? So socket.write, and say something like welcome socket.name, just like that. So now that we have a name for every socket, we can actually use the name here instead of the ID to identify the socket. Socket.name in here. And I think we can test. Connect 3 clients, and you'll notice how the server is asking for the name. Let's name the first chatter Alice, Bob for the second, Charlie for the third. And you see how the server welcomed the names. So now when Alice types something, Bob and Charlie get the message Alice said hello. Let's try it here. So Bob is saying hi, Charlie is saying hey. So that's a good improvement. How about we also show the timestamp of the message? Because without timestamps, it's not really a chat server. So we can simply display the timestamp here right after the name. So let's make it into a variable. And how about we create a function for the timestamp, just like that. And let's go define this function. So function timestamp is a very simple function that will basically format the current date. So let's do now equal new date. This is to just give me the current date. And let's return a string that has the hours, which is now.get hours, and the minutes, which is now.get minutes. Very simple. So this would be like HHMM format. This is very simple. If you really want to do an actual time format, you have to handle multiple cases and you have to be aware of time zones and all that. I would recommend a library called Moment if you want to actually work with timestamps, but this is just an example to improve our simple chat server. So let's test that. Alice, Bob, and Charlie. Now we see that Alice said hello at 10:47. Let's take a look at the DNS module. We can use it to translate network name to addresses and vice versa. For example, we can use the lookup method to look up a host, say pluralsight.com. This gives us a callback, error first callback, and it gives us the address for that host. So we can log the address here. And running this will give us the IP address for pluralsight.com. The lookup method on the DNS module is actually a very special one because it does not necessarily perform any network communication and instead uses the underlying operating system facilities to perform name resolution. This means that it will be using libuv threads. All the other methods on the DNS module uses the network directly and does not use libuv threads. For example, the equivalent network method for lookup is resolve4. 4 is the family of IP addresses, so we're interested in IPv4 addresses. And this will give us an array of addresses in case the domain has multiple A records, which seems to be the case for pluralsight.com. If we just use resolve instead of resolve4, the default second argument here is A, which is an A record, so this is what just happened. But we can also resolve other types. Like, for example, if we're interested in the MX record, we just do that. And here are all the MX records for pluralsight.com. You can tell they're using Google Apps. And all the available types also have equivalent method names. So MX here is the same as resolving with the MX argument. Another interesting method to know about is the reverse method. The reverse method takes in an IP. So let's actually pass one of the IPs for Pluralsight, and it gives us a callback, error first, and host names. So it translates an IP back to its host names. Let's test that, and you'll notice that it translates this IP back to an Amazon AWS host name. If we actually try to open this in the browser, it will probably go to pluralsight.com. There you go. Let's see an example for working with UDP sockets in Node. To do so, we need to require the dgram module, which provides an implementation for the UDP datagram sockets. We then can use the dgram create socket method to create a new socket. The argument for the create socket could be UDP4 or UDP6, depending on the type of socket that you want to use. So we're using UDP4 in here. And to listen on this socket, we use server.bind and give it port and host. I'm putting port and host here in constants because I'm going to reuse them for the communication. So the server object here is an event emitter, and it has a few events that we can register handlers for. The first event is the listening event, which happens when the UDP server starts listening. And the other event that we want to register a handle for is the message event. This event happens every time the socket receives a message. Its callback exposes the message itself and the remote information. So let's console log the remote information address and port and the message so that we know where the message is coming from. And that's it for the UDP server. We can actually run this code and the server will start listening for connections. So this part is the server, and I'm going to create a client in the same file here for simplicity. So since we do have this dgram required already, and we can actually share these 3 variables, so all we need to do is we need to create a client socket, which we can use the same call for. Let's call this client. And to send a UDP packet, we can use client.send. This method takes the first argument can be a string. So let's send plural site rocks. And we need to tell the UDP socket which port and host to send this message to. So we can use port and host in here. And this exposes an optional callback in case we want to handle the error in here. So if there's an error, we should throw it. And in here, we can console log something like UDP message sent. And potentially after we send this message, we can close the client in case this is the only UDP packet that we want to send. So we can test that. You'll see that server is listening, message is sent, and you'll see this code is getting fired with the right address port in there. Every time you create a new socket, it will use a different port. For example, let's put all this code in an interval function, and every second do all of this sending. Let's see what happens now. You'll see that every second we're getting a different port for the remote information. Let's undo this. So back to sending a message. This first argument here is currently a string, but it can also be a buffer. So let's create a new buffer. I'm going to call it message, and it will be buffer from this message. And I want to send this message, which is a buffer in this case. And when we have a buffer, we can specify where to start from this buffer and where to end from this buffer. So 0 and message.length will be equivalent to sending a string. So you'll see I got the same thing in there. So we're sending the buffer from 0 to message.length, and I can actually send the packet in multiple steps. So for example, let's send the first 11 bytes, which is plural site. And after we do that, let's send from 11 6 characters, which is going to give me the rocks message. So let's take a look at that. Now you'll see that the packet was sent on 2 steps. So we have pluralsight in the first step and then space rocks in the second step. Let me undo that because we don't need it. So specifying an offset and a length is only needed if you use a buffer. The first argument can actually be an array of messages if we need to send multiple things. In this module, we explored Node capabilities for working with TCP and UDP networking. We created a basic network server example using the net module and saw how we can communicate with TCP sockets for read and write and how the sockets are event emitters. We saw how to give every socket an ID and how to keep a record of all connected sockets, and then we used that structure to make our network server into a simple chat application. We then improved that chat application by asking connected clients about their names first and outputting a timestamp for every chat message. We then explored the DNS module and its various methods and how to use it to translate network names into addresses and vice versa. And finally, we saw an example for working with UDP sockets in Node using the dgram module. In the next course module, we'll talk about Node's HTTP and HTTPS capabilities. HTTP is a first-class citizen in Node. In fact, Node started as a web server and evolved into the much more generalized framework it is today. Node's HTTP module is designed with streaming and low latency in mind. Node is today a very popular tool to create and run web servers. Let's look at the typical Hello World example for Node's HTTP module. We create a server using the HTTP module createServer method, which gives us, no surprise there, an event emitter object. That event emitter has many events, one of which is the request event, and this event happens every time a client connects to this HTTP server. It exposes a request object and a response object. We can use the response object to modify the response Node will be using for that request. In here, we respond with 200 OK, content type text, and the text hello world. The server runs on port 8000. When we run the script, Node will not exit because it has a listener handler and it will respond to any HTTP request on port 8000. If we inspect the headers this simple HTTP server is sending, we'll see HTTP 1.1. This is the current most recent version of HTTP that's supported in browsers. Response code is 200 OK, and the content type is what we set it to. And we have a connection keep alive and transfer encoding is chunked. Keep alive means that the connection to the web server will be persisted. The TCP connection will not be killed after a requester receives a response so that they can send multiple requests on the same connection. Transfer encoding chunked is used to send a variable length response text. It basically means that the response is being streamed. Node is okay with us sending partial chunked responses because the response object is a writable stream. There is no response length value being sent. After Node sends the 200 OK here, it can do many other things before terminating the response. And instead of inefficiently buffering everything it wants to write in memory and then write it at once, it can just stream parts of the response as they're ready. So this very simple HTTP server can be used, for example, to stream video files out of the box. But remember that the connection is not terminated here. So the browser knows that the content is done through the HTTP protocol. HTTP 1.1 has a way of terminating a message, and it's what happens when we use the response.end function. So if we actually don't use the end method, if we use the write method instead, in this case, when a client connects, they get the hello world, but the response is not terminated because basically Node is still streaming. In fact, in here, we can define a timer function. Let's make that fires after 1 second. And inside this function, we'll go ahead and write another message. And how about we write yet another message after 2 seconds? Let's try it. Run the server, connect, and you'll see hello world. After 1 second, you'll see another message. And after 2 seconds, you'll see the third message. And the server is still streaming. We have not instructed HTTP to terminate the response object. Let's make the timeout periods here a little bit longer. Let's do 10 seconds and 20 seconds and test that. Initiate an HTTP request. I see the hello world. Node is not really sleeping, it's just idling. It can actually handle other client requests during this idling phase, thanks to the event loop. Both of these requests are being handled concurrently with the same Node process. Please note, however, that terminating the response object with a call to the end method is not optional. You have to do it for every request. If you don't, the request will time out after the default timeout period, which is set to 2 minutes. As you can see, this write line did not happen because it's delayed to after the default server timeout. We can actually control the server timeout using the timeout property. So this line will make the timeout 1 second, and you'll see now how the server is going to time out right away. HTTPS is the HTTP protocol over TLS SSL. Node has a separate module to work with HTTPS, but it's very similar to the HTTP module. To convert the basic HTTP server example to work with HTTPS, all we need to do is require HTTPS instead and provide the createServer method with an options object. This object can be used to configure multiple things. Usually we can pass key and certificate. Those can be buffers or strings to represent a private key and a certificate. We can also pass a PFX option to combine them if we want. I'll just use key insert, and let's walk through a complete example. We first need to generate a certificate. We can use the OpenSSL toolkit for that, which allows us to generate a private key. We can have it encrypted or not encrypted, and it allows us to generate a certificate signing request and then self-sign this certificate to test it. Of course, the browsers will not trust our self-signed certificate, but it's good for testing purposes. We can actually combine all these steps with one command that will output a private key and a certificate file for us. It will ask for some information, but since it's all just a test, you can use the default answers here. When this command is done, you should see a key.pem file and a cert.pem file in the working directory. Now that we have these files, we just need to pass them here to the createServer method. We can use the fs module to do that. We'll do read file sync. Since these files are to be read once and used for creating a server, this is okay here. We'll do /the key.pem file, and same thing for the cert. So it's cert.pem. And of course, we need to require the fs module. And the last thing we need to do is to change this port to 443, which is the default port for HTTPS communication. To test all that, we need to execute the script. In my environment, I need to sudo this command to get access to the 443 port. So sudo node HTTPS, and we have an HTTPS server. So we can go to HTTPS localhost, and the browser is going to warn us about the self-signed certificate. It simply means that the browser does not recognize this certificate, but we can trust it manually. And there you go. Very simple. Node can also be used as a client for requesting HTTP and HTTPS data. There are 5 major classes of objects in Node's HTTP module. The server class is what we use to create the basic server. It inherits from net server, so it's an event emitter. A server response object gets created internally by an HTTP server. The HTTP agent class is used to manage pooling sockets used in HTTP client requests. Node uses a global agent by default, but we can create a different agent with different options when we need to. When we initiate an HTTP request, we will be working with a client request object. This is different from the request object we've seen in the server example. That request object is actually an incoming message object, which we're going to see in a little bit. Both client request and server response implement the writable stream interface. Incoming message objects implement the readable stream interface, and all 3 objects are event emitters. We've seen the basic server example. Let's see a basic request example. Let's request the HTML page at google.com with Node. We can use the http.request method. This method takes an option argument, and it gives us access to a callback with the response for the host that we're going to request. We can specify many options here. To request google.com, we need hostname is google.com, and we can use multiple other options here. For example, the default method is get, but we can use a method like post if we need to post information to a hostname. I'll leave it default, and in here we can console log the response, which is going to be the HTML at google.com. You'll notice one thing about the handler that we define in the second argument here. It doesn't have an error argument. It's simply because that this handler gets registered as an event listener, and we also handle the error with an event listener here. So this HTTP request method returns an object, and that object is an event emitter. So we can register a handler for the error event. So we can do something like request.onError and handle the error in that case. So we can do something like this. Since this request object is a writable stream, we can do things like write. For example, if we're writing with a post method. But for get requests, we don't need that. We just need to terminate the stream. So we do .end here. And that should do it. Let's test. So node request, and I'll pipe it on less. And you'll see the response object here is an incoming message. So we can read information on this response object like status code. We can also read response.headers, for example. And this response object is an event emitter. It emits a data event when it receives data from the hostname. This data event gives us a callback, and that callback's argument is a buffer. So for example, if we want to see the actual HTML, we'll do toString on it. So let's actually take a look at that. You'll see the status code 200, the headers object, and you'll see the actual HTML for google.com. If we're not writing any information to the headers request, if we're not posting or putting or deleting data, we can actually just use the get method here. This get method is simpler. Its first argument is just a string with the URL that we want to read. So we need to add the HTTP protocol in here. And we don't need to do request.end on this. That will be done for us. So this should be equivalent. And this request is done using the global HTTP agent. So the HTTP module has a global agent, which Node uses to manage the sockets here. It has some pre-configured options here. We can see that agent information here if we do request.agent. So in here, you'll first see the agent information, and then you'll see the printed information from the response. And all this interface is exactly the same if we want to work with HTTPS instead of HTTP. So if we want to fetch HTTPS google.com, all we need to do is replace HTTP with HTTPS, and things will work exactly the same. But it's now communicating the request over HTTPS. So let me now show you where to identify these objects in the examples we've seen so far. In this example, the request object here is from the class client request. This response object is of type incoming message. And the agent that was used for the request is of type HTTP agent. In the server example, the server object is from the HTTP server class. The request object inside the request listener is from the incoming message class, and the response object is from the server response class. Let's see how we can work with routes using Node's HTTP module. We have the basic server here, and what I want to do, I want to support some routes. Let's try to support a home route, an API route, and see how we can respond to different things in there. So to support that, we need to first read the URL information, and this is easy. We can use request.url to do so. So now, when I request localhost, the request.url is /, and anything I put here, I will be able to read it. So to handle routes, all we need to do is we need a switch statement for this request.url. So, for example, what should we do when it's /? Or what should we do when it's home? And so on. So let's assume that we have a home.html file, very basic template HTML, and we want to display this file when we go to /home. All we need to do is write the header, which is in this case text HTML, and then in here, we want to read home.html and write it to the response. So we can use fs.readFileSync /home.html. And of course, we need the fs module. And let's try it. There you go. Excellent. What if we have an about.html, and now we also want to support /about? So it's the exact same code as this portion, so we can actually make it dynamic. Let's make it support both home and about. And let's make this part dynamic, because this is the exact request.url part. So first convert this into a template string, and then this part becomes variable request.url, just like that. Let's test. We can now see the about page and the home page. So what should we do on the root route? How about we redirect the user to /home? With Node, we just write a header for that. So it's write head, and we'll use 301 here to indicate a permanent move. And the header that we want to write here is the location header. So this is permanently moved to /home. And we still need to end the response. So now, when we request the / route, it will tell us that it was moved permanently to /home. By the way, this first number here is the HTTP status code. We can actually take a look at all the status codes using http.statuscodes. So you'll see all of them here. 301 is moved permanently. If you need to work with JSON data, say that we have a route here, we'll make it /API. So this route is going to respond with some data. Let's assume that we have the data here in a constant. This data is some kind of object, and we want to respond with this data as JSON. So we need to do two things. First, the content type in this case is application/JSON. And the information that we want to write here is a stringified version of the JSON object. So it's json.stringify the data variable. And we can test that. So in here, if we go to /API, we'll get back a JSON response. Now, what happens if we request something that does not exist? Right now, the server does not respond with anything, and it will eventually time out. So this would be this default case here. So we should probably respond with 404 in this case. So 404 means not found. We should still end the response here. So it's right now, it will give me a 404 not found. If you need to work with URLs, especially if you need to parse URL, Node has this URL module that you can use. It has many methods, but the most important one is parse. The format method is also useful. So let me show you how to work with that. Before we do, let's take a look at the URL API documentation from the nodejs.org website. This diagram here has details on all the elements of a URL. This example is manually parsing this URL in here. So you can see we have the protocol, which is HTTP. There is the authentication part, which is username and password in case we have those. Then there's hostname and port, and both of them together is a host. Then there is the path name, which is what comes after the host and before the query string. And then with a query string, the question mark including the query itself, we call it search. But without the question mark, we call it query. And path name plus search is called path. And if we have a hash location here, it will be called hash. These are all the elements in any URL object. So if we have the URL as a string and we need to parse it into those elements, we can use the URL parse method. For example, I can use the URL.parse method to parse this URL that I just grabbed from Pluralsight search. And this call is going to give me all the elements that I have in that URL. We have an HTTPS protocol. We don't have any authentication data. The host is pluralsight.com. And since the port is null, the host and hostname is the same. There's no hash. There's a search part, query part, path name, path, and the href itself, which is the full URL. We can actually also specify a second argument here, true, to parse the query string itself. So if we do that, the query string will be parsed. And reading information from the query string is as easy as doing .query.q, for example. This will give me exactly the search query for that URL. If, on the other hand, you have the inverse situation, if you have an object with all these elements detailed and you want to format this object into a URL, you can use the URL.format method. And this will give you back a string with all these URL object properties concatenated in the right way. If you only care about the query string, then you can use the query string module, which has many methods as you see, but the most important ones are the parse method and the stringify method. So if we have an object like this one, and we want to convert this object into a query string portion, all we need to do is call query string.stringify on that object, and it will give me an actual string I can use in any URL query. And you can see how this stringify method escaped some special characters by default, which is great. If you have the inverse situation, if you have a query string and you want to parse it into an object, what you need here is query string.parse, and you give it the string that you want to parse, and this will give you back an object parsed from that query string. In this module, we talked about the basic Node's HTTP server and how it's non-blocking and streaming ready out of the box. We saw how to create an HTTPS server with a test self-signed certificate that we created using the OpenSSL kit. We reviewed the 5 major HTTP module classes and identified them in the examples we used. We saw how to use Node for requesting HTTP and HTTPS data from the web. We also talked about how to support basic web routes using Node's HTTP module. We used that to respond with HTML files, JSON data, and to handle redirects and not found URLs. Finally, We explored how to parse and format URLs and query strings using the native Node modules provided for them. Let's explore some of the common built-in modules that comes with Node. Node provides a number of utilities to access information directly from the operating system. We can use the OS module for that. We can read information about CPUs like their model, speed, and times. We can read information about network interfaces. We can read their IP addresses, but we can also read the MAC addresses, net masks, and families. We can read information about total and free memory. Where is the OS temp directory? And most importantly, what operating system was Node compiled for? The type method will return Linux or Windows NT, or Darwin for OS X. We can use that method, for example, to write code specific to an operating system. We can also read the release version of the operating system with the release method. The user info method is a handy one. It returns an object with information about the current user: username, UID, GID, shell, and home directory. On Windows, the shell attribute is null, and both UID and GID are -1. os.constants return an object with all the operating system error codes and process signals. The signals list is a handy, quick way to see a reference of all process signals available in the underlying OS. The FS module provides simple file system I/O functions to use with Node. All the FS module functions have asynchronous and synchronous forms. You can pick either form depending on your code logic. For example, if you're reading a file during a server initialization process, read file sync is probably okay. But if you're reading a file every time a user requests something from that server, you should probably stick with the asynchronous form. Other than being synchronous or asynchronous, those forms handle exceptions differently. The async functions pass any encountered errors normally as the first argument in the callback, while the synchronous functions immediately throw any errors. When using the synchronous functions, if you don't want the errors to bubble up, you'll need to use a try-catch statement to handle them. The readFile method, by the way, gives back a buffer if we don't specify a character encoding, which we can do in the second argument if needed. I usually default to working with buffers unless I have specific needs to convert the raw data into a string. To explore the multiple capabilities of the FS module, I thought we'd go through some realistic tasks and demonstrate how to do them with the FS module. For the first task, we have a directory full of corrupted files. Someone accidentally ran a script that appended a copy of each file to itself. So each file has its data duplicated, and you're tasked to write a Node script to fix that, basically to truncate each file to half its content. I have prepared some bad data doubled files for you in this task 1 files directory. As you can see, the https.js file, which was our HTTPS example, is duplicated here. And all the other files in this directory have the same problem. Go ahead and try to write that script on your own first, then come back to see my version of the solution. Pause the video here. To fix a list of files, we first need to read that list. The readDir method can do that for us. I'm using the sync version of this method here because basically this script has nothing to do unless we have a list of files. Once we have the list of files, this files constant will be an array of file names. Just the names, not the full path. So we'll use the path module to get the actual full path. Don't use string concatenation here. Always use path.join when working with file paths to make your code platform agnostic. For every file path, the goal is to truncate it to the right size, which is half of its current size. So we need to read each file size. We don't need to read the file content. We just need its size. So instead of using readFile here, we can use the stat method, which gives us only meta information about the file, including its size. Note how here we used the asynchronous versions of the methods because we have multiple files to process. Once we have the size, we can use the truncate method with exactly half the size of the file. Problem solved. To test this script, we just run it in this task1 directory, and then we'll make sure that the files were fixed correctly. And looks like they did. The second task, you have a directory with many log files, and you're tasked to write a Node script that is to be run every day on that directory and it should delete all files older than 7 days. So just keep 1 week worth of logs in that directory. You don't have access to that directory, so your task includes generating test data to make sure your cleaning script is working correctly. Want to try that task on your own first? Pause here. Here's our test data seed script. We first synchronously create a destination directory to work with. We can't do anything without that. Then, with a simple for loop, we'll create 10 sample files using the write file method. And then for each file we create, we use the uTimes method to change its timestamp. This method takes 2 arguments after the file path, the access time and the modified time. We're just using the same value here. These 2 arguments expect a Unix timestamp in seconds. I wanted every file to have a different timestamp, starting from the current date and going back to 9 days in the past. So I subtracted 1 day milliseconds multiplied by the current file index value, which is 0 through 9. I then divided the whole thing by 1,000 to suit the arguments for the uTimes function. The result of running this script is a new files directory with 10 files, each with a different timestamp. File 0 is current date, file 1 is 1 day old, and so on. Now that we have our test data, let's write a script to clean any files older than 7 days. Basically, our script should remove files 7, 8, and 9. The solution is simple. Exactly like task 1, we need to loop over all the files in the directory. And we need to read the stats metadata for each file. What we're interested in now, however, is the mtime for every file. If the file was not modified in the last 7 days, we want to delete it, which we can do with the unlink function. The if statement here is simple. The mtime is a date object, so using the getTime method, we read its Unix milliseconds value. Subtract that from the current Unix millisecond value and check if the result is greater than 7 days in milliseconds. When we run this script, files 7, 8, and 9 will be deleted. If we run the script again, no files will be deleted. And if we run it tomorrow, same time, file 6 will be deleted. Task 3. You're tasked to write a script that watches one directory and log 3 types of events on that directory. When a file is added, removed, or changed in the directory, your script should output a timestamped message about that event. We can simply use the fswatch for this task. But fswatch does not give us enough details to account for all 3 events. Both the add and delete events are reported under the watch method as rename event type. Here's what I did to work around that. For testing, the files directory is what we'll watch, and it has 3 empty files. We first read the names of the current files in the directory to be watched. Then we start the watch listener. If the event type is rename, it means a file was either added or deleted from the directory. So if the file exists in the current files array, it means the event is a remove event, and we update our current files array to remove the removed file. The log with time method just outputs the message with a UTC timestamp. If we get to this point in the code, it means a file is being added. So we'll update the current files array and log that message. If the event type is not rename, the other event type supported in this listener is the change event. So in this case, the file is being changed. The fswatch API is actually not completely consistent on different environments. So be sure to test any code written with it thoroughly first. To test this code, we simply run this file, and then we'll try to do some changes on our test files. So I'll go ahead and change file 0, and we get file 0 was changed message. And let's go ahead and try to delete file 0. And we'll get file 0 was removed, and we'll create a new file, and we get the file 0 was added message. The console module has some interesting less known parts that I want to make sure that you know about. The console module is designed to match the console object provided by web browsers. In Node.js, there is a console class that we can use to write to any Node.js stream, and there is a global console object already configured to write to stdout and stderr. These are two different things. So for example, if you want to use the console methods, but instead of writing to stdout and stderr, you want to write to, say, a socket or a file, all you need to do is instantiate a different console object from the console class and pass the desired output and error streams as arguments. When we run this code, for example, it'll create an out.log and error.log files and write to both of them every 5 seconds. Console.log uses the util module under the hood to format and output a message with a new line. We can use printf formatting elements in the message, or we can simply use multiple arguments to print multiple messages on the same line. Popular formatting elements are %d for a number and %s for a string. There's also %j for a JSON object. If you want to use the printf substitutions without console log in it, you can use the util.format method. This just returns the formatted string. We can console log objects, and Node will use the util.inspect method to print the string representations of those objects. Util.inspect has a second options argument that we can use to control the output. For example, to only use the first level of an object, we can use a depth 0 option. Util.inspect just returns the string. If you want to use the inspect second argument and still print to stdout, you can use the console.dir function. It'll pass the second argument option to util.inspect and print out the result. Console.info is just an alias to console.log. Console.error behaves exactly like console.log but writes to stderr instead of stdout. Console.warn is an alias for console.error. The console object has an assert function for simple assertions to test if the argument is true. It will throw an assertion error if it's not. The built-in assert module has a lot more features for assertions, and I usually use it for quick assertions. It's not perfect, but it's good enough for simple cases. The if-error function on the assert module is a particularly interesting one. It throws value if value is truthy, which is exactly what we usually do on any errors argument in callbacks. Console.trace behaves just like console error, but it also prints the call stack at the point where it is placed, which is handy when debugging problems. You can use console.time and console.timeEnd to start and stop timers and report the duration of an operation. The argument you pass to them should be a unique label for that operation. The util module has a few more handy functions. There is debug log if you want to conditionally write debug messages to stderr based on the existence of the node debug environment variable. This debug line here will only be reported if this script was executed with node debug equal web. The util.deprecate function can be used to wrap a function, say before you export it, to mark that function as deprecated. Users of that function will get a deprecation warning the first time they use that function. Finally, the util.inherits method was heavily used before the introduction of ES6 classes to inherit prototype methods from one constructor to another. However, with ES6 classes and the extends keyword, the use of this util.inherits methods is no longer needed or recommended, but you'll probably see it a lot in older examples of Node code. Node comes with a built-in debugger that supports single-stepping, breakpoints, watchers, and much more. In here, I have a simple function that I expect to calculate the negative sum of all its arguments. So when we call it with 1, 5, and 10, I expect the result to be 0 minus 1 minus 5 minus 10, which is minus 16. The implementation is simple. We reduce the arguments starting from 0, and every time we just subtract the argument from the running total. However, the script is not working as expected. So I'm going to use the built-in debugger to step through this code and try to find the problem. We activate the debugger by simply adding the debug argument to the command line. When we do that, you'll notice how the debugger is listening on this port. Node basically communicates with the debugger on this port. You can type help to see what you can do. Familiar debugging commands like continue, next, step are all available. Node starts the debugger session in a break state, so we always need to continue execution. If we type in continue now, the script will simply run and output the wrong answer and be done. We don't have any breakpoints. We can actually place a debugger line anywhere in the script, and when the debugger reaches that line, it will halt, allowing us to inspect that point in code and issue other commands. Since we reached the end of this script and did not really step into anything, let's start over using the restart command. This time, before continuing the execution, we'll set a breakpoint on line 2 using the SB command. This is equivalent to adding a debugger line on that point. Now that we have a breakpoint, we can continue the execution with the continue command. The debugger will break at that point. We can now inspect anything accessible to the script at that point using the rebel command. We can, for example, inspect the args variable, which appears to be correct, so it seems our problem might be inside the reduce callback. So let's create a breakpoint in there, line 3. Now the debugger should break 3 times there because we're looping over 3 arguments, but instead of manually inspecting the variables on every break, we can define watch expressions using the watch command. I'd like to watch the arg variable and the total variable. We now have 2 watchers that will be reported when the debugger breaks. When we continue, the watchers report arg to be 0 and total to be 1, which is actually flipped. I'm expecting total to start with 0 and arg to be the first argument in the array, which is 1. So to verify, let's continue again. Total is now getting the 5 value, which is the second argument in the array. And if we continue again, it's getting the 10. So I definitely got the order of the callback arguments wrong. It should be total first and arg second. Easy fix. If while debugging you cleared your screen, I can do that with Control L here, and you can't remember where exactly the debugger is currently breaking, you can use the list command, which takes an argument of how many lines it should list before and after the current breakpoint. This debugger client is not perfect, but it's good enough for a quick interactive debugging session. But it gets better. Recent Node versions support an experimental feature to integrate the Chrome dev tools to debug any script. All we need to do is use the -- inspect argument with the script. But this feature does not break by default, so we can use the -- debug break argument to make it break before the first execution. When we add the -- inspect argument, we get a URL to open in Chrome. And when we open that URL in Chrome, DevTools will open our Node script, and we can use all the familiar fully featured tools here to inspect the script. We can step into an over functions. For example, to redo our debugging session here, I can simply step into -sum, and while I'm stepping over the 3 reduce calls, I can see the argument values right there without any need to watch or set breakpoints. But if I need to set breakpoints, I can simply do that by clicking on the line numbers here. I can also use the console to inspect any variables or expressions, and I can even hover over variables to see their current values. So all the features that we know and love in Chrome DevTools can now be used with Node scripts, and the best thing about it is that it's all built in. I don't need to install any packages to get this value. When I resume the execution of this script, the console log call on line 7 will be reported here. In this module, we explored the native OS module that can be used to access information directly from the operating system. We then explored the various synchronous and asynchronous capabilities of the FS module by implementing 3 practical tasks. We've seen how to use the methods to create a directory, read directory information, read file stats, truncate a file, write to a file, update the last modified time of a file, delete a file, and watch as a file or directory for changes. We explored the methods on the console objects, like log, error, trace, and the use of time end to report durations of executions. We saw how we can create a custom console object, and saw how the console object uses the util module internally and that we can use the util module directly if we need to. The util module has some extra utility functions that are helpful, like the debug log, for example, to control debug messages in your code, and the deprecate function to mark pieces of your code as deprecated and give the users a warning when they use them. We debugged a problem in a script using the built-in debugger client and saw how we can set breakpoints, define watchers, and inspect any point in the code using a built-in REPL. We've also seen how we can use the Chrome DevTools to debug our Node script using the -- inspect argument, which gives us a much better graphical client to debug our Node code. Work